Hey Chem 240 students, this is Dr. Ricardo. This is the first video in chapter 20, which is on electrochemistry. So these are the formulas that we're going to use over the course of the chapter. Some of them you see kind of look familiar, some of them don't, but I wouldn't worry about those now, but we'll get back to them later. And something for you to have available for you when you're studying chapter 20, you should have these out when you're doing the homework. Okay, so a quick review of oxidation and reduction, because it's been a long time since you talked about this in Chem 1. So we're going to talk about oxidation reduction reactions, which really are electron transfer reactions. So first thing we have to realize or remember is how to calculate the oxidation number or the oxidation state on a particular chemical species, either in an element or a chemical compound. So let's read the definition. The oxidation number or oxidation state is the charge on an atom in a substance. The charge an atom in a substance would have if the pairs of electrons in each bond belong to the more electronegative atom. So if this bond was not shared equally, who would have the extra electron? In this case, chlorine is much more electronegative than hydrogen, so chlorine would have a -1 and hydrogen would have a +1. And we learned that just by using the oxidation states that are on the periodic table, you learn that chloride, when you think about it, is -1 and hydrogen's typical oxidation state is +1. In water, the oxidation state on oxygen is -2, that's its normal oxidation state, and hydrogen is +1. So if you take those two +1s together and the -2, you get 0. Okay? So these electrons, if they broke down the middle, this would go off as an H dot and an OH dot. But if they were going to break heterolytically, and this bond would break, it would be the oxygen that would be more likely to take the two electrons, leaving this as the hydrogen ion, which is very typical, and the hydroxide ion. Okay? Here's the ionic compound iron, Roman numeral 2 chloride. I know it's Roman numeral 2 because the charge on the iron is +2. I could have gotten that because chloride's only negative oxidation state is -1, and there were two chlorines. So in order for this to equal 0, the chlorine had to be +2. Excuse me, the iron had to be +2. So this is the oxidation state on iron in this particular compound. And the last one, the oxidation state on an element is always 0. So in chlorine is a diatomic element. It's one of 7 elements that always double up, right? So in Cl2, each oxygen is 0, right? In hydrogen, each hydrogen is 0. On oxygen, there's 0. All of those typical diatomic elements, right? Fluorine, bromine, iodine, I think that's it. Okay, so those 7 things, 1, 2, 3, 4, 5, 6, 7, they love to double up. If they were to split, each one would be 0. Okay, here's an unusual case. This is hydrogen as a nonmetal. So if this would break, it's actually less electronegative than sodium. So sodium would leave with the +1 state, and hydrogen would leave with both of the electrons and making this H-1. So here, hydrogen is written on the right-hand side. It's typically in the form of the metal. It's written on the left-hand side to the left of a typical metal like sodium. It would be a hydride and be -1. Last example, what is the oxidation state of carbon in carbon dioxide? Well, since carbon is together with oxygen, oxygen is always a -2, right? So if each oxygen, if oxide, and why is this in the oxide form? Oxygen is to the right of chlorine on the periodic table. It's also to the right of it in the compound. And the normal thing that oxygen does is go to the -2 state. So if each oxygen is in the -2 state, and there are 2 of them, 2 times -2 gives you -4. So that -4 has to be balanced by something because the whole carbon dioxide is equal to 0. So that carbon dioxide has got to be, the carbon in carbon dioxide has got to be +4. Since there's only one carbon dioxide, that's the answer. It's also +4. right? So the ones I put up here are the charges on each, the ones I'll put in the boxes, those could be the charge on all of that species. So this carbon has got to balance this 2 oxygen, so it has to be +4, and there's only 1, so the oxidation state on carbon and carbon dioxide is +4. So that should be a little bit of a review. Okay, here's some examples of assigning oxidation numbers to atoms in compounds or ions. So the first one is perchloric acid. So the H is written out front, okay, so it's in the metal position. This is not a hydride. The only time H would be on the other side or would be negative if it was with a metal, and there's no metals in here. So chlorine is more electronegative and oxygen is more electronegative, okay. So, in fact, oxygen is the most electronegative thing in this species. So oxygen is going to go to its typical oxidation state of -2. There are 4 of them, so 4 times -2 gives you -8. We know the hydrogen is +1, right, because it's the least electronegative, and that's hydrogen's typical oxidation state. So if this guy's +1 and this guy's -8, and the whole thing equals 0, because I didn't write anything up here, right, that little 2 is for the oxygen, for the oxides. Then what is chlorine? Has to be 7, because it's what number? +1 equals -8, and the answer is 7 + 1 balances -8, right? So this plus this plus this has to equal 0 because there's no charge. Okay, this compound is called potassium dichromate. Potassium is the metal. You can go to the periodic table and find its typical oxidation state. It's going to be typically +1, okay? It's always +1 whenever it's in a chemical compound. The only time potassium would be 0 is if it was in potassium metal, just like this, K solid, all by itself. That would be potassium in the 0 state, a metal all by itself. But we don't have that. It's in a chemical compound. So if it's +1, and there are 2 of them, 2 times +1 gives you a +2, so this part is +2. Then we go over to the oxygen side. Each oxygen is -2 for the same reason it was up here. It's the most electronegative element, and oxygen is, unless it's in peroxide, which this isn't, is going to be -2. So -2 times 7 gives you -14. Then we ask ourselves, what do these 2 guys in the middle have to be so that the whole thing equals 0? Well, if this is -14 and this is +2, this has to be +12 because 2, 12, and -14 equals 0. Well, if both of them are +12, what's each one? Each chrome is going to be +6. So the oxidation state on each chrome is going to be +6. So that's the answer to typical multiple choice questions. What is the oxidation state on chrome in potassium dichromate? The answer would be +6. Okay, let's do this ion, right? These 2 down here are ions. So how do you handle ions? Well, the way you do it is, for ions, you are not trying to make the total charge equal to 0. You're trying to make the total charge equal to the overall charge on the ion. So the overall charge on the ion, sulfate, is -2. You guys know that, right? If the whole thing is -2, okay? Each oxygen is more electronegative than sulfur. Whenever oxygen is written to the right in anything, it's going to be -2, and this is no exception. These are oxide ions. So at -2, and each one is at -2, and there are 4 of them, all 4 oxygens equal -8. So then we have to ask ourselves, what must this one sulfur be so that when I put it together with -8, I get a -2. I got to put it together with -8. Okay, so what do I have to put here together with -8 so that the whole thing equals -2? And the answer is +6. It's +6 and -8 would give you -2. So that's the charge on sulfur. The oxidation state on sulfur in sulfate is +6. This is the most oxidized you'll ever find sulfur. If you look on the periodic table, it has choices, but the most positive one will be +6. Okay, here's permanganate. So permanganate is MnO4 - 1. It already has a -1 charge. So I'm not trying to get everything to add up to -1, I'm trying to get everything to add up to, excuse me, I'm not trying to get everything to add up to 0, I'm trying to get everything to add up to -1. Okay, again, regular oxygen. Oxygen is more electronegative by a lot than manganese, so it's going to be holding the negative charge. The ordinary state of oxygen is -2. -2 times 4, because there are 4 of them, gives you -8. So what must the manganese be so that the whole thing adds up to -1? +7 and -8 add up to a -1, right? Don't try to balance it out. If I was going for 0, it would be +8 and -8. +7 and -1 add up to the charge on the whole thing, which is -1. So answer to the question, what is the oxidation state on manganese in permanganate? Boom, +7. Okay, just a review of what the charges are in these typical compounds. This is lead chloride. We'd call it lead Roman numeral 4 chloride. How do I know this? Tin, not lead. How do I know this tin is in the +4 state? Well, I know the tin is in the +4 state because, we got a lot of lightning outside. Okay, hold on one second. Let me just close my window so you don't have to hear a big lightning storm. It's actually, besides lightning, it's actually a little bit of hail outside. Okay, so chloride is much more electronegative than tin, so it has to be its only negative oxidation state, which is -1. Well, if there's 4 chlorines at -1, then the tin has to be at +4 to balance it. So these aren't just the oxidation state, this is the actual charge as well. Okay, but again, what would the question be? What is the oxidation state on tin in tin chloride? And the answer is +4. Well, here's tin Roman numeral 2 chloride. Well, since there's 2 chlorines at each one at -1, the tin's got to be +2 to balance it. Okay, phosphorus Roman numeral 3 oxide. Okay, so what's happening here is I've got 4 phosphoruses. All right, let me get a different piece of paper. Wow, some storm. So here I go, I got P4O6. So each oxygen is -2, right? The whole thing is a big fat 0 because there's nothing written on it, right? If nothing's written out here, you're adding up to 0. Where here, they were adding up to -2 and -1. So if they're adding up to 0, 6 times a -2 is -12. So that means all of those 4 phosphorus together have to be +12, right? Well, 12 divided by 4 is equal to 3, right? Each phosphorus has to be a +3. So the oxidation state on phosphorus in P4O6 is +3, okay? And the last compound, what about this one? P4O10. Again, oxygen is all the way, I'm going to get a different pen. Oxygen is all the way on the right-hand side, right? So it's minus, it's in its typical oxidation state. So each oxygen is -2, and there are 10 of them. So 2 times 10 is equal to a -20, right? So these guys are -20. They all have to add up to 0. What do all 4 of the phosphorus have to be to add up to 0? Well, they have to be +20. If I have 4 things that are equal to +20, what's each one? Each one has to be 5 because 20 divided by 4 is 5. So somebody asked you, what's the oxidation state on phosphorus in tetraphosphorus decaoxide or phosphorus Roman numeral 5 oxide? The answer is +5. Okay, let's take a look at some oxidation reduction reactions. Okay, first of all, the definition of an oxidation half reaction is the part of the reaction, if you split them up into the side that's donating electrons and the side that's receiving electrons, the oxidation state is going to be the side that's donating electrons. In general chemistry, the definition of oxidation is the loss of electrons. We don't count the oxygens per se. That's more of an organic chemistry way of looking at it. Anything that loses electrons is oxidation. Now, it does turn out that when something gains oxygens, since oxygens themselves soak up electrons, they tend to cause other things to do what? To lose electrons. So oxidation is not only the loss of electrons, many times it also results in becoming oxygenated, having more oxygens on you at the end. Okay, but for us, we're going to go right to following the electrons. Oxidation is the loss of electrons. Reduction is the gain of electrons. Okay, so if electrons go in and the thing becomes more positive than it used to be before, that's a reduction. This name reduction comes from the charge being reduced. If you gain an electron, you're a chemical species, and you have a charge, right? Let's say your charge is 0. If you add on an electron, you become -1. What happens to your charge? It went from 0 to -1. That's a reduction. The numbers are going to go down. That's why we call it reduction. Okay, here's an example. Take this molecular reaction. Okay, the molecular reaction, I'm going to see if I can get this to be a little bit better. Let me autofocus, maybe that helps. Okay, the molecular reaction is the reaction of iron plus copper sulfate solution. So I take a piece of iron, like an iron, a nail, and I put it into a copper sulfate solution, which is a beautiful blue solution. What's going to start to happen is that the solution is going to change from copper sulfate to iron sulfate, so the blue is going to go away, and it's going to be replaced over time by kind of an ugly red color, and that ugly red color is just going to come from it looking like rust, because iron in the +2 state is going to be reddish, or actually more yellowish in this case, so that's what you're going to get. So as the copper disappears, the blue from the copper +2 goes away, and I start to form copper on the outside of the nail. So that would be really cool. The iron is going into solution, and the copper would be coming out, just like you think of copper as in copper pennies. Okay, well, we can break apart this chemical reaction in the following way. First thing we can go is from the molecular reaction to the ionic reaction, then to the net ionic reaction, then we can break it up into oxidation and reduction. So the ionic reaction is anything that's ionized, that's dissolved in solution, break it apart into its corresponding ions. So iron we leave alone because it's solid, but the copper sulfate, I break it apart into copper +2 and sulfate -2. That makes sense because this is really dissolved. It really exists in solution as this and this. Okay? Same thing with the iron sulfate here, right? Iron sulfate in solution exists as independent little ions. So I get Fe+2, right, because the charge on iron is +2. Why do I know that? Because sulfate is always -2. That's, you have memorized that sulfate is -2, right? And then there's the sulfate with the -2. And the last thing, leave copper alone because it's a metal. So I leave this guy alone and that guy alone, and I break apart these ionic salts. Okay, next thing, net ionic reaction. Cancel out anything that's found in exactly the same way on the left-hand side of the equation and the right-hand side of the equation. Look at these two sulfates, right? On this side, it's being created, but then it's quickly being used up, so they cancel out. So I wind up with those guys being gone. Those are called the spectator ions, the things that disappear. You remember that from Chem 1. So what's left? Just the real reaction has nothing to do with sulfate. Sulfate's got nothing to do with it. It's copper +2 ions smash into the iron nail, steal 2 electrons from them, plate out as copper solid, and force the iron nail, one atom of the iron nail, to become iron +2. So it's an exchange of 2 electrons, right? Which way are the 2 electrons going? They're going from the iron to the copper. How can I tell that? Because the copper, right, is gaining 2 electrons, so it had to lose the electrons from the iron. Okay, so the last step after you write the net ionic reaction is break it up into the oxidation half reaction and the reduction half reaction. Okay, remember, you're never going to have one of these by itself. We're never going to have oxidation independent of reduction. They have to take place in pairs. Kind of like acids and bases, right? Whenever we had an acid, we also had a base, right? And they reacted with each other. to either neutralize each other and make water and a salt, or a strong acid and a weak base would react with each other to make a weak acid and a strong base. So they would kind of switch partners. But there was always an opposite guy. You can't have one without the other. Same thing with oxidation and reduction. You can't give up electrons unless someone's going to capture it. They don't go flying into midair and make sparks. All of the electrons that are lost by the iron are gained by the copper. So here's what happened to the iron. I write down its two species, and then I put in the number of electrons that are necessary to get this to balance. Look, this is iron plus 2. Plus 2 electrons goes to iron solid. What about the copper? I wrote down the copper plus 2 and the copper solid. Then the copper plus 2 had to gain 2 electrons, right, to get to 0. Now, after I do that, cool thing that I see is when I add back the 2 half reactions, this will always happen, add the oxidation back to the reduction, and I'll get the net ionic equation back. That's how you know you did it right. Add the half reactions to get the net ionic equation back. Okay, here's another example. This is the example that happens when something rusts, right? So I have iron solid, right? Iron is originally in the 0 state. Any element already has all of its electrons. It's in the 0 state. It's going to react with oxygen. This is also an element, so it's in the 0 state. They react to make iron oxide, right? This is the typical version of iron that you ordinarily find in rust. Okay, it's iron in its most stable oxidation state, the +3 state. How could I get this +3 up here? You guys can see it a little bit, it's in red. Okay, see this guy was 0, this guy was 0, this guy is +3, right? Well, this guy's +3 because if I crisscrossed, this 3 would come up here and this 2 would go there, and that would make sense because iron, everything's got to balance out. It's got no charge in the rust, right? This is just what you think of as red rust, right? Red powdery rust. It's got it's got a total charge of 0. So the +3 of the iron times 2 gives you +6. The -2 of the oxide times 3, 2 times 3 gives you -6. Well, that makes sense. Okay. So what happened here? Okay. Well, we're not so worried about the creating of the iron oxide. That's kind of the byproduct at the end. Let's follow the electrons. If I have iron going from iron to iron +3, that is a 3-electron oxidation. Your job is to tell me that you realize that this is oxidation. Oxidation is the loss of electrons. 0 to +3 is a 3-electron what? A 3-electron oxidation. What did the oxygen do? I have 2 oxygens in O2. Each one is at 0. At the end, it creates 2 oxygens, each one. Okay, don't worry about this 3 now. We'll take care of that in a minute. Okay, because there's really our 6 here. Okay, we're just following the separate steps. Okay, each oxygen in the iron oxide goes to -2. Okay, so I have 2 oxygens at 0 going to 2 oxygens at -2. How did that happen? Well, the only way that can happen is if each oxygen gained 2 electrons and split with the other oxygen. So 2 go to the one on the left, 2 go to the one on the right. It's a 4-electron reduction. Again, oxidation is the loss of electrons. Electrons are the product. Reduction is the gain of electrons. Electrons are the reactant. Okay? If I put those 2 things back together, I probably have this at the top of the next page. Let me just see. Okay, I do. Okay? If I put those 2 things back together, I say I have a 3-electron oxidation and a 2-electron reduction. Well, they have to match up, right? All of the electrons that are lost in the oxidation have to be gained in the reduction. So what do I have to do? I have to take the guy with the 2, right? Let me try to see if I can get both of these on the same page. Okay? I have to take the guy with the 3 and multiply it by what? I have to multiply this one. I have to multiply this guy by 4 and this guy by 3, because 4 and 3 are going to get together at 12. I have 12 electrons participating overall. Okay, so let me see if I go ahead and do that for you, because that's a little bit hard to follow. So back here, I had my Fe goes to Fe plus 3 and 3 electrons, right? And we said that's oxidation. And then here I have my O2 plus 4 electrons go to 2 oxides, and that's reduction. Okay. Well, from a first glance, right, this one up here though, yeah, from a first glance, I should be able to do it just at 6. I don't see why I have to go to 12, so let's see what happens with that. So this is a 3 electron process, this is a 2 electron process. I have to balance all of the electrons that are oxidized with all of the ones that are reduced. Oh, I see why. This is a 4. Okay, so if this is a 4 and this is a 3, what's the first place where 4 and 3 get together? They would get together at 12, right? That's what they have in common. So how do I get this guy up here to 12? Multiply everybody through by 4. 4, 4, and 4 times 3 gives me 12. So this is a 12 electron oxidation. Okay, this one down here, how do I get it to 12? Multiply everybody through by 3 of these. 4 times 3 is 12 of these. 2 times 3 of these is 6 of these. So the 12 electrons have to cancel out. And then I have 4 irons that go to 4 iron plus 3s. 3 O2s that go to 6 O minus 2s, right? So that's what this looks like at the end. All the electrons must cancel out in the net ionic equation. And then I just put together this 4 of these and 6 of those, and they would make 2 units of Fe2O3, right? Because the 3s can only get together with the 2s if I have 2 of these and 3 of those, and then I'm going to have a double set of that. So the electrons drive the fact that this had to go up, not just to multiply through this one by 2 and this one by 3, but I had to multiply this one by 3 and this one by 4. Okay, so it's all about getting every single electron to cancel. You can't have oxidation without having reduction. Okay, whenever there's a species that's oxidized, right, there must be a corresponding species that's reduced, right? They always go together. So what are we going to call them? Well, the thing that's oxidized causes something else to be reduced, right? So the reducing agent is the species that reduces another species, so it must be oxidized itself. So everything is opposite. If I'm the reducing agent, okay, if I'm the reducing agent, I'm getting oxidized myself. If I'm the oxidizing agent, I myself are being reduced because I caused someone else to be oxidized. Let me see if I give you a football analogy. The greatest agent for a quarterback is a great receiver, right? So the receiver, right, if you're a great receiver and you're always open and you catch everything that the quarterback throws to you, even if it's a little bit off, he or she doesn't throw the best pass, but you're such a good receiver that you catch it anyway. Well, you make that quarterback look great, and they make millions of dollars. So the receiver is the quarterback agent. Okay, how about if you're not such a great receiver, you hardly get open, but you have such a great quarterback that he or she can get the ball into you in the tightest of spaces and make perfect passes, so you're making all these catches. Well, the greatest receiver agent is a quarterback. So it's always opposite. So let's take a look at this. To me, the thing that's being oxidized is the quarterback. Here's the quarterback. The quarterback throws the passes, right? So iron itself throws 2 passes, it gets oxidized to iron plus 2. So that's the oxidation. What happens to copper in this reaction? Copper gains 2 electrons. It's like the receiver. It's going to catch 2 passes. Catches 2 passes, it itself is being reduced. Iron, which is being oxidized, is called the reducing agent because it made copper plus 2 look so good as a receiver. Okay? Copper plus 2 is the oxidizing agent because it made iron get oxidized. It helped in the process to cause the other guy to get oxidized. So you see what happens with the agents? They're opposite to what happens to the chemical species themselves. Okay. This is something that you may remember from Chem 1, okay, not super important to what we're doing, but there is something called the activity series, which is a table that lists the element in order of their ease of losing electrons during a reaction in aqueous solution. So the ones that lose electrons the easiest are the easiest to oxidize, right, must be the strongest reducing agent. And I have a table like this that they use for Chem 1 that I'll show you in a second. So those are going to be things like the alkali metals and the alkali earth metals when they're in their metallic form. They lose electrons so easily that they cause something else to be reduced. So they're the easiest to be oxidized, so they're the best reducing agents. Okay? The harder something is to oxidize, you're a terrible, right? You don't want to get oxidized, then you're not going to cause anything else to get reduced. So you're the weakest reducing agent. Okay, so let me show you that before I go on and do this last little piece here, which is on disproportionation. So I'll grab one of those tables. You guys may have seen this in all different forms. Here's one. Usually we think about it for single replacement reactions, which is what you're going to see in a lot of these. Okay, so the most active, easiest to oxidize metals are lithium, rubidium, potassium, calcium, sodium, group 1 and group 2 metals. Aluminum sneaks in there, then magnesium, zinc, iron, nickel, tin, then lead, copper, silver, platinum, and gold. These are great at oxidizing, right, which means they're great reducing agents. These guys down here, gold, is terrible at being oxidized. Therefore, it can't reduce anything, which is good. We don't want gold to react. That's why we make our jewelry out of it. So the precious metals are unreactive substances, right? So, and hydrogen would fit in right in between these two. So in the sense of hydrogen losing electrons and going from H2 to 2 H pluses, how easy that is for it to happen would fit right in here after lead, okay? So it's a little bit harder for this to happen than for lead to go to lead plus 2, okay? And for the nonmetals, it's going to work the other way. You remember that? This guy is the one that's the most easily reduced. Therefore, it's a fantastic oxidizing agent, okay? It has to gain electrons to go from F2 to 2F minus to go to fluoride ions. Chlorine less so, bromine less so, iodine less so. So great at being reduced, makes it a fantastic oxidizing agent. Terrible at being reduced, makes it not terrible at being a oxidizing agent. Okay, so that's the way they go. But we're not going to use this as much as we're going to use another table that actually gives you the E0 for these reactions. So we can actually quantify them instead of just comparing them. Okay, this is kind of cool. This is the last topic here. And that is this idea of disproportionation. And this happens a lot. Okay, so what's going to happen is you're going to have a chemical species. It's going to be in a certain state. And there's going to be more than one atom of that element. And one of the atoms is going to get oxidized while the other one gets reduced. So here's the definition. Disproportionation is the reaction in which a species is both oxidized and reduced. Not the same exact atom. You need to have two of them, right? One of them is going to go up, the other one is going to go down. In a sense, they're almost going to steal electrons from each other. So if I have two copper plus ones, now copper plus one is a kind of metastable state, okay? Copper would rather be copper metal, right? That's pretty stable. You have pennies that last hundreds of years. Or what it really would like to be is copper plus 2. So if I have copper 1 around, it's not going to last very long. It's going to actually react with each other, right? One of them is going to go from copper plus 1 to copper 0. Well, that is a reduction. I have to gain an electron to do that. And the other of the two coppers is going to lose its electron and get oxidized to copper plus 2. Well, how did that happen? The two of them, one of them smashed into the other, and one stole an electron from another. The one who's doing the stealing is the one getting reduced. The one who's being stolen from is the one that's being oxidized, right? Because oxidation is the loss of electrons. Here's another example. So we know chlorine gas is used as a disinfectant, right? So you can chlorinate water supplies. Well, chlorinating water supplies by bubbling in gaseous chlorine gas, which is dangerous, okay, reacts because it reacts with the water to make hydrochloric acid, which isn't really the dangerous part of this. This is the dangerous part of this. This is, hypochlorous acid, which is the active ingredient in bleach. So it's this one in water. This guy is the species, and this guy who does the disinfecting, who kills the microorganisms. And the way they kill the microorganisms is they oxidize the heck out of the microorganisms, stealing the electrons from the microorganisms, and they die. And that's good because we want to kill the bacteria that's in the water supply or whatever other bad things are in there, viruses. So chlorine is both reduced to HCl and oxidized to hypochlorous acid in this case. So let's try to follow that. I've got two chlorines, they're both at 0, okay? Come over here. This chlorine now winds up as -1. So the first one that goes from here to here, what had to happen to you? I had to gain an electron to go from 0 to +1. That's reduction, okay? What happened to the other one? The other one went from chlorine to chlorine +1, right? This is an oxidized version of chlorine. It's a reactive version of chlorine. This guy's done when it gets to -1, right? It's toast. It's at the end of the chain of oxidation. This guy is now very reactive at +1. Okay, honestly, even more reactive than this. So here it is at +1. What happened from here to here? I had to lose an electron to go from 0 to +1. So I was oxidized. So this is a disproportionation of chlorine. One goes to -1, the other one goes to +1. Okay, so chlorine is both oxidized and reduced. Okay, in the next chapter, we're going to look at oxidation reduction reactions involving not just the simple ions, but these oxyions, the ions that have a lot of oxygens attached to them. So here's a typical example. Okay, the bromine reaction is simple. I have 10 Br minuses, so that's bromine in the -1 state. And they're going to make 5 Br2. So they're going to make bromine in the 0 state. And then bromine is diatomic, so the individual 10 atoms are going to hook up into 5 sets of 2. They love to be paired up. Okay? Well, what happened to the bromine? If I go from -1 to 0, the only way I can do that is to lose electrons. Each bromine loses 1 electron. So this is a 10 electron oxidation, the loss of electrons. Okay, what's happening to permanganate? This is permanganate in the, it's a little hard for you guys to see, but this is in the +7 state. Okay, so it's in the +7 state. Here, it winds up as manganese in the +2 state. Well, that's a 5 electron reduction. I have each manganese at +7. Each one gains 5. If I'm at +7 and I gain 5 electrons, I go to manganese +2. But that happens twice. So 2 times 5 is 10, so that makes sense. I can't have a 10 electron oxidation without a corresponding 10 electron reduction. Okay? And the waters are going to, and the hydrogen ions are just going to be along for the ride to do the balancing. The meat of the reaction is this oxidation and this reduction. One thing that I don't like about what I have on here, I'm going to take it off right now with some whiteout, is I don't like my double arrows. I want to get rid of the arrow on the left-hand side, right? What is that doing there? Let's look at this as I start out over here and I make my way over to here. Same thing over here. I don't want a double arrow. I want to start out over here and I want to make my way to the other side. So when I go from here to here, that's a 5 electron reduction. Okay, that's it for this video. That's 40 minutes. That's probably perfect. Next, we're going to pick up on chapter 7 and I'm going to teach you how to balance redox reaction.